Guess we should go ahead and get started. We're more or less done with chapter 20. I just wanted to show you a few critical things regarding chapter 20. And I already worked like up through example 3, but I want to reiterate what I hold you responsible for from a testing standpoint, not from homework and not from practice tests, which hopefully I've gotten rid of most of them, of the ones that aren't needed in the practice test banks, but I'm not sure that I have. So I do not expect you to have to do a lot of the stuff from chapter 20. I do expect you to know that the Boltzmann constant K times the ln of W is a function that represents the entropy S. Uh, even though I'm not planning on making you use it, you should know that that is a definition of entropy. I'm not even really requiring you to be able to calculate the entropy change from one reaction to another, or from one process or another, or stuff like that. I really just expect you to be able to calculate the efficiency of any heat engine, the Carnot efficiency of any heat engine, as well as the coefficients of performance for air conditioners, refrigerators, and heat pumps. So I thought I'd work a couple more examples like that before we jump into chapter 21, which is largely about electricity. So we're starting on that today, and hopefully at the end. If not, we might just have to save it till next time. But I wanted to point out exactly what the coefficient, or excuse me, what the coefficient of performance is for refrigerators, air conditioners, and heat pumps. So your book actually does a really good job of explaining exactly how a refrigerator works, as well as how a heat pump works, as well as how a freezer works. Just a freezer and refrigerator are about the same thing. It's just what I noticed, for instance, in my personal refrigerator, is that it gets all the cool into the freezer area, and then that same mechanism that blows air takes the remaining fluid and blows it into or the remaining fluid in the sense that it's further down the line, blows across those sinks, if you will. They're just, huge things that are freezing cold. Wind blows across it, and it releases cold air into the room. What basically happens is a good fraction of the cold air is completely blown out before it ever gets out of the freezer. It's all blown into the freezer, and then whatever's left gets some of the refrigerator. So the refrigerator is just a moderately less cold area than the freezer. Even though you have some adjustment on how much that is, in terms of adjusting the temperature of the thermometer, as well for the freezer, as well as adjusting. I said thermometer, but I meant thermostat, as well as being able to adjust the temperature of the refrigerator. So I do recommend you read that. I do recommend you read, for instance, the section about the OTTO cycle, because that is the one that's closest to a gas engine. But again, I'm not requiring you to do any of that either. You just need to know that the Carnot efficiency from the Carnot theorem basically is the most the most efficient calculation of efficiency you can get from any heat engine, period. So any of those model heat engines like the Otto cycle, or the Stirling engine, or the Carnot engine, all of them will basically have a maximum efficiency that's given by 1 minus T low over T high. But all heat engines have an efficiency given 1 minus Q low over Q high. So that's part of the main thing about the Carnot statement of the second law of thermodynamics, or the Carnot theorem, which is roughly about the second law of thermodynamics. Specifically, Carnot says every heat engine operating between TL and TH will have the same efficiency as the Carnot engine. And that means a reversible one. So it's like all ideal reversible engines will all have an efficiency given by 1 minus TL over TH. And every non-reversible or irreversible engine, which means real engines, will always have an efficiency less than that. So you do have to calculate those, but you also have to calculate the coefficient of performance for those various things. So I wanted to let you know what the diagram is, for instance, of the heat engine process that is a freezer, for instance. So let me show you a quick drawing regarding that, and then the formulas accordingly. So what we have in principle And I'm going to go ahead and share my screen with you. Almost forgot for a second there. I'm going to go ahead and share my screen with you. And here it comes. Hopefully. So you can sort of think of a refrigerator or an air conditioner or even a heat pump in some sense like it's engine running backwards. So we have a temperature TH of a hot heat reservoir. Okay. And we have a pipe that's actually feeding that heat reservoir. And that heat reservoir is connected to a cold temperature reservoir, which has a temperature, let's call it T low. And that's, again, another heat reservoir. But what we have going on here is a heat engine, in this case, running, like I said, in reverse, will be represented by this figure. And I think it's probably best if I label it like this. Okay. And now what we're going to see is a certain amount of heat, QL, will go into the air conditioner, refrigerator, whatever, in that case. But also work will go into it like this. And then a amount of heat, QH, will be expelled into a hot reservoir. Now, in the case of a refrigerator or freezer, the hot reservoir is essentially the kitchen or whatever room you've got it mounted in. In some cases, it might be your garage. I know some people have multiple refrigerators like myself. I got one in the garage and one up here in the kitchen, that sort of thing. So that's sort of what we're shooting at. But what you need to see is there's a certain amount of work done by the refrigerator, and that is, all the bells and whistles. But from a cooling standpoint, it's basically the compressor and the condenser. So the compressor is actually attempts to pressurize the working substance, which used to be Freon, but it's various other Freon like chemicals that we use now. But the main thing is the compressor would compress them, and then they would get extremely hot, partly as as a result of the compression, and then those heat sinks on the back, which in some refrigerators it's literally out on the back, so you see all the little wires connecting and all that stuff. That's where the heat escapes from the working fluid through those metal tubes on the back of your refrigerator or down below your refrigerator. And then it hits a release valve, and that release valve actually opens it up into a very, very low pressure reservoir that's also created by the compressor. Specifically, when the compressor has the piston up, it's just finished compressing the working substance. Then it pulls down. That decreases the pressure by a great deal, and that causes a gas that goes through the relief valve will actually condense out into a liquid and be super, super cold because it's just extracted heat from the environment to make it condense out. The environment being the inside of the refrigerator in the case of a refrigerator, or the inside of the freezer in the case of a freezer. But for a heat pump, it would be just taking the energy from inside the house and taking the work from the light receptacle slash power company, and then putting that all that heat out either into your attic or out into the outdoors or both. So that's what a uh, air conditioner slash refrigerator slash freezer does. Uh, and their coefficient of performance for such a thing is what you get divided by what you pay for. So again, we have E is what you get divided by what you pay for. Well, what you're getting is how much heat is removed from inside the refrigerator or inside the freezer or inside the house, and that quantity is QL. And then what you pay for is the W. In other words, the work that your compressor does via the electricity provided from the power company. Now, in principle, remember this diagram also shows the same conservation of energy equation that we had for heat engines, specifically that QH is going to equal W plus QL. So you could ultimately say this would be QL over QH minus QL. And that should be the actual equation for the coefficient of performance, not the efficiency. I did say efficiency, and I even wrote efficiency, but I wanted to make sure you realize it is something different. It's called the coefficient of performance, and I made a cross through it and show you its COP. Now, with that in mind, there's a nice new statement of the second law of thermodynamics. It says no device is possible whose sole effect is to transfer heat from one region at a temperature TL into a second region at a higher temperature TH. So that's basically the same thing I'd showed you on the notes last time, which you recall wasn't that. Maybe it was this one. Yeah, this thing right here down at the bottom, that TH with the QH going into it, and no excess leaving the heat engine, which is the green box. So it's just QH all turning into W. Well, now you can imagine all the W coming in and taking basically not dumping any QH out or something like that would be another diagram for you to consider. Now that I have that, let's go ahead and do an example. Oh, I should also say that there is, based on what derivations we did with the Carnot engine, there is sort of an ideal coefficient of performance, and that ideal coefficient of performance, COP ideal, basically hinges on our realization that we can change QL over QH with TL over TH, and therefore this whole equation now becomes TL over TH minus TL. So that's the ideal one. But to be honest with you, I don't think I've ever had you do anything but homeworks with that. I've never even questioned or put one of those questions on the test. But you should be able to know how to calculate the coefficient of performance for these devices. So I'm going to show you an example now. Uh, Example one. Okay. A freezer, in this case, a freezer, has a coefficient of performance. Has a coefficient of performance, which we just call COP, even though it's technically an acronym, so it's supposed to have periods and all that good stuff. But we're going to say it has a COP of 2.6. That's a bad looking six there. Of 2.6, and it uses about 300.0 watts of power. And that means obviously from the power company, more or less, to run the compressors and all that good stuff. What we would like to know is how long will it take to freeze 1,000. Now let's just say, yeah, let's say 0.500 kilograms of water at 0.00 degrees Celsius. Okay. So that's our problem. We're trying to figure out, basically how quickly it'll take to freeze a half a kilogram of water. So our process is this solution, which is where I normally sort of explain to you what equations we can use or should be using and what method we're going to go for. What we're using is the fact that the COP is equal to the heat removed from the cold areas divided by the work that's put in. And in this case, we see that the work actually put in. Oops, someone's coming in. There it is. Finally got it. Uh, so what we're trying to do here is we're trying to realize that the actual work done is the 300 watts. So we can imagine that as a per second reading. And what we do is we say the COP is equal to 2.6. The work is equal to 300 point zero, and I'd say joules per second because we're going to focus on the actual work as opposed to the actual power. So I really should call that just joules, but I'll say 300 joules each second. Okay. Now that we have that, we can go in a search for QH, which would be how much heat would be dumped out and that sort of thing. But more specifically, we can find out exactly like how much heat QL is removed, and that's what we need to figure out to realize how long it's going to take to freeze the ice. So, first off, the Q that must be extracted from the ice has to be equal to M times L because we're not changing the temperature of the ice. We're just trying to take the ice at zero, the water that's at 0 degrees Celsius, and make it into ice at 0 degrees Celsius. And the formula for that is M times the latent heat of fusion. In the case of actually going from a liquid to a solid or a solid to a liquid, and in the case from going from a liquid to a gas, that would be vaporization. So we're using the fusion one, and that gives us 0.500 kilograms times 333, uh, and that is times 10 to the third joules per kilogram. So we can basically take 333,000 and multiply that by zero point 0.5, and that gives me 166,500 joules, and only three of those digits are significant, so it's the 166 that's significant. Now we know that's how much energy we need to freeze that much water into ice. Now we got to figure out what QL is, and according to the COP equation, QL should be equal to W times the COP, and the W we said was 300.0 joules, and the COP was 2.6. So that gives us 300 times 2.6 equals 780 joules. Now remember that that figure was 300 joules every second because they said 300 watts. So we are removing 780 joules each second. If all of that was focused on just the ice, then all we have to do is, since power is equal to energy divided by time, then we can say time should just be the energy required divided by the power. So what I'm going to do is I'm going to take the energy that's required, which is 1,600 or 166,500 joules, and I'm going to divide that by the 780 joules that occur each second, and that'll just give me seconds. So if I take this 166, if I take this 166,500 and divide it by 780 joules per second, that gives me 213.5 seconds. Now 180 seconds is 3 minutes. So, excuse me, 60 seconds is a minute, 120 seconds is 2 minutes, 180 is 3 minutes, and 240 would be 4 minutes. So we're not quite there, but at 3 minutes we'd be 180. So we're 3 minutes and 33 seconds, so about 3.5 minutes. Any questions on that one?
No,
All right, that's cool. Thanks you for answering me.
you're welcome.
Uh, do you have any questions since now you and Josh came in? I asked questions before y'all got here, but like I said, y'all weren't here. So if you have any questions you want to ask me, you can ask me now before I go into my next example.
No, you're good. I'm fine.
Okay, that's cool. Now, when we do a heat pump, it's a little different scenario. So I want to show you what a heat pump does. This was refrigerator and AC. Hopefully, I can spell refrigerator properly. Actually, let me see. I'll double check, make sure. I always want to put a D somewhere in the middle of the refrigerator, which is not necessarily the right place. But anyways, refrigerator and freezer. Okay, so now I'm going to do a heat pump. Oops. You guys might be uh, slightly old enough where you've actually had to purchase a heating unit before or something like that. If that's the case, then you've probably heard at least some negative press about heat pumps. But all they are really is we're used to more like gas packs, I think is one of the phrases they use, where they can use liquid propane or some other type of gas that would actually just burn like a flame, heating up various pipes with liquid in it. That pipe with liquid would float around and come into some area where you can blow heat around it. That's the heat exchanger area. And if that's the case, that's where we get our heat from. In this case, we're doing a heat pump, which instead of using gas, just use nothing but electricity to extract heat from the ambient air inside the building or the house or whatever, and then releasing it to the outdoors. So with this sort of design, your book actually did a neat little job where it made one of those little schematics, but they made a schematic that was for indoor of a house versus outdoor of a house. So I kind of like it. So I'll show you. Actually, I'll give you an idea roughly what it looks like. So you can imagine, for instance, that there is a heat engine that's going to be this green rectangle here, and it's right on the interface uh, between the house and the indoors. So I'll say like this is the inside of the wall, this is the siding on the house, and this is the inside of the wall. So inside, where the temperature is actually kind of warm, we'll say T hot is in here, and what we're actually doing is we are forcing a certain amount of heat to come from the outdoors, which I'm going to say comes in like this. So this side of it here is out. Oops, I want to do that in yellow. Uh, is outside. And what we're trying to do, of course, is get that heat, which actually I think I drew that line a little larger than it should be. Let's do this. Obviously, it's not that critical that these lines be perfect, but I am, I am who I am. So now I'm going to take the other side, which is just to show how much heat is coming in. This is heat that we're taking from the really, really cold outside. So this would be QL, and it's being fed into the heat engine, which obviously is like running backwards. But out here, the temperature is T low, which is supposed to be cold. Now, in addition to this Q low that it gets in, we also have a certain amount of work being done, and that amount of work being done is W. And what we say now is the heat combined with the QL combined with some of the W possibly results in QH going into the house. Okay, so that's supposed to be the inside the house versus the outside the house. Now, from this, you should be able to see that efficiency, which again I said was E, but we're really calculating coefficient of performance. So this coefficient of performance in this case is supposed to be what you get, and that's really how much heat you're putting into the house. So that's QH divided by what you pay for, which is again W in this case. And again, you can see that QH has to be equal to the work put in plus QL. So you can again call this QH over QH minus QL. So that is the coefficient of performance for a heat pump. So notice the difference between that and the refrigerator, which remember the refrigerator is literally trying to take cold air from a cold place and put it into a warm place, whereas a heat pump is doing the same thing, but the part that really matters isn't how much heat we removed from the cold place, but rather how much heat we got into the hot place. So that's why the QH is on top instead of the Q low on top like we had here. So hopefully that makes some sense to you guys. All right. Now that we have that, we can attempt another example. So let's say this will be example 2. In this case, what we're going to say is a heat pump has a COP of 3.0 and is rated at 1850 watts. We want to know A, how much heat can we remove or add to a room per second? In 1 second. And then part B, they want us to try and figure out what the coefficient of performance would be if it was ran backwards. Ooh, I can't fit backwards in that space. And of course, we're running it backwards, basically assuming that it's an air conditioner. So we'd say as an AC. So that's what we're shooting for. Again, solution, what we need here is the coefficient of performance for the heat pump. So I'm going to say COP HP is QH over W, which of course is also equal to QH over QH minus QL. But we're also going to need the coefficient of performance if we're using for the freezer or excuse me, for the air conditioner when we're running it into backwards, and of course the coefficient of performance for that guy, which is again for AC, is going to be QL over W. So that's what we're going to use here. We've already got that our work is equal to 1850.0 joules each second. So we have that, and we have that the COP for the heat pump is 3.0. So now we can use it as follows. Let's do part A. Part A, we need to find out exactly how much heat is being put in. And since we have the work per second, then this will be the amount of heat per second. So the QH in solving for COP, QH is equal to W times COP for the heat pump. And W, of course, is 1,850 joules each second, of course, times the coefficient of performance, which is 3.0. So if I multiply these two numbers, I get 3.0 times 1,850. That is 5,550. And obviously, we only have two sig figs now, but that does come out in joules. So that's actually our QH, and that's what they were asking in part A, which was specifically how much heat can we actually add to the indoors in a second. So that's 5,550 joules. Now for part B, what we're going to try to do is calculate what the coefficient of performance is for it run as an air conditioner backwards. So we're still going to use all the other things that are the same, only now we're going to say it's QL over W instead of QH. Well, once we had QH and we had W, we knew that QH is equal to W plus QL. So that implies QL has got to equal QH minus W. So we can go ahead and take the 1850 and subtract it from the 5,550. So that gives us 5,550 joules minus 1,850 joules divided by 1,850 joules. And with that in mind, we end up getting that the coefficient of performance for this AC is actually equal to 5,550 minus 1,850 is 3,700. I'm going to divide the 3,700 by 1,850 joules, and that gives me a coefficient of performance that's equal to 2.0. So that's another example that you should be able to solve, of course. You need to know how to use these coefficients of performance for freezers, refrigerators, air conditioners, heat pumps, and then, of course, for the heat engine, you need to know the efficiency. Any questions on that one? Your book does take the time to explain to you what the SEER reading is, so you might have heard that if you ever hear on the radio. Occasionally, I'll hear a HVAC commercial by Michael and Sons or somebody, and they'll talk about one. They often talk about tonnage, which your book's not talking about anywhere that I know of, in anyways. But it does talk about the SEER rating, and the SEER rating is really supposed to be the heat removed in British thermal units. But here's the weird part: they're using British thermal units for the numerator of the SEER, but the denominator is the actual electrical input in watt hours. So you have to take basically how much power rating the actual unit has, which would be measured in watts. Actually, you might expect it to be in BTUs or something like that. But the main thing is you could get it to BTUs per second, which is equivalent to joules. But in this case, we really want the actual, or is equivalent to watts. But actually, we want the joule reading basically, because you're going to take the watt, which is joules per second, and multiply it by 3,600 seconds, which would be a watt hour. So that's kind of nice to have, but that's the SEER rating. I'm not requiring you to do any kind of calculations with it, but I wanted you just to understand that that's exactly what it is. Any questions on that as we move on?
No.
Okay. So the other section that we go into after this air conditioners and heat pumps and all that good stuff is basically a section where we introduce the concept of entropy. And entropy, I want you to know about, specifically, I want you to know that entropy is S and the variable S. And of course, it's measured, which you'll see in a second as proof of that, in joules per Kelvin, but it's defined as delta S, the change in entropy, is equal to the heat added or taken away here. This is important. Once we get into entropy in your textbook, we're no longer using the idea that we learned in the Carnot engine and the coefficients of performance, where QH, QL, and W are all positive. Now we're going back to the normal definitions of Q and W, which means if heat is being added to the system, then Q is positive, and if heat is being taken away from the system, Q is negative. If work is being done by the system, then work is positive, and if work is being done on the system, then work is negative. So we now have, using those sign conventions, that if you actually add an amount of heat Q at a constant temperature T, then you will have a change in entropy given by delta S equals Q over P. Okay, so that's sort of our defining equation. Of course, not all processes take place at a constant temperature, so you've got to be able to deal with that as well. So often what we do is we'll end up saying delta S, which equals S final minus S initial. And really, to be honest with you, it's the S, the change in S that matters, just like the change in potential energy is what mattered back when we first studied conservation of energy. But either way, we're going to get by saying basically the integral of that statement is in some sense d bar q over t, and we take the integral from the initial state to the final state. The nice thing about the entropy is it's what we call a state variable. And a state variable is really nice. Those variables and those state functions, for instance, are the functions that meet some very specific criteria that we'll learn about a lot in electricity and magnetism. Specifically, if you find such a thing like a state variable, then you can take it in any cycle that you want, meaning starting from point A to point B, and then C and D and E and F and J and all that. But if it comes back to state A at the end, then that's a cycle, meaning it's going to repeat itself. It can repeat itself next. But the important thing is that is always equal to zero for state variables. Not only that, the integral of this from, let's say, A to B is actually independent of path. So that's another characteristic of state variables. And they have that exact differential equation that you can associate it with. Like you could say S is a function of, let's say S, just for the heck of it, is a function of pressure, volume, and temperature, something like that. And let's say also number of moles. Then what that means is ds would be the partial of F with respect to P times dP plus the partial. I said S, but I wrote F, or actually I think I might have said F. That might have been why I wrote the F. But anyways, it should be a S. So it's the partial of F with respect to V dV plus the partial of F, excuse me, I said F again, of S with respect to T dt plus the partial of S with respect to N dn. So that's one of the other ramifications of something being a state variable. But the most important part about that being a state variable is when you actually do handle a more robust treatment of entropy, what you know is if you have an initial state and a final state uh, that you need to go to, then all it takes, since the entropy is a state variable, all it takes to calculate the change in entropy from that initial state to that final state is any path that you can find that gets you from that initial state A to that final state B. whether it's the real path or not doesn't matter at all, including even perfectly reversible ones. You can use those all day long and calculate the change in entropy. And since it only depends on the final and initial conditions, which state variables do, then you'll automatically get the right answer. So that's kind of the nice part of it. But that's what entropy is. It's also considered a measure of disorder. So you might have heard that before yourself. I don't know how I just got to that page, but that's interesting. Okay. You might have I forgot what I was talking about with regards to you might have run into it before or whatever. But anyways, once you have that entropy, it is a measure of disorder. And if you've heard that phrase before, it's probably best that you put some meat on those bones because it's very hard to make the logical conclusion from disorder to entropy without a little bit more fuller explanation. So the explanation I often give people is imagine for a second that I'm going to draw a really nice perfect shape. I'm going to say this is a rectangle, and that rectangle specifically is going to represent a car. So one of the ways we can think of that's not really a good square. That's really aggravating. No, that's not it either. Let's see. There you go. That's a good one. So let's delete that thing. Oop, I can't delete it. Never mind. I can just erase it this way. So if you imagine this is actually a car, and let's imagine that we have a parking space, which this car was 5 blocks long. So I'm going to make this 7 blocks long. And it was 3 wide, so I'm going to make this 5 wide. 5, like that. So there's your parking spaces. Okay. And what you can do is you can say a measure of the disorder of something is the number of different ways you can put it in that situation that are all still satisfying all the criteria of that particular process. So in the process of parking, a parking I'm trying a hard time selecting this. A parking success is anything that has this car inside the red line. So that's one parking success. This is another parking success. This is another. This is another. This is another. This is another. This is all those are no, are other ones, as well as this one. Just shifting it over a little bit. This one, 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 this. So you can see all these different ways you could park in here, and I haven't even shown you the ones where I could actually try to rotate this thing. Oops, that was a bad move. Where I could actually try rotating it back and forth like this, as long as all four corners are in between these three lines, then you still have a valid parking space. You've parked it validly, I should say. So what we look at in terms of disorder is how many different ways can you satisfy the criteria. In this case, the criteria was being parked. How many different ways can you be parked? And it's literally counting all those infinite number of ways this car can fit into that space. Now, when you go and pull out of a parking space, which is usually a lot easier than parking in a parking space, the reason why that's a lot easier is because you're going with the second law of thermodynamics, because this is a valid place, this is a valid place, so we're looking at just the places that are valid for removing from a parking space. So all these different places are, basically ways you could pull out of the parking space. In fact, it could go here, 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 and it gets a little wider as you go about here, 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 all those different spaces. Obviously, there was an infinite number in the first case though you couldn't necessarily access them because you probably don't have the ability to drive a car down to millimeter precision. But in principle, there's an infinity of places. And yes, there's an infinity of places outside of the parking space, but I think everybody realizes that the number of parking spaces or the number of places outside of the parking space you could pull into is way, 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 way bigger than the number inside. So you can use that the second law of thermodynamics to explain why it's harder to park than it is to get out of a parking space, and that's because you're going from a state of high entropy, which is where you'd be, or in this case, you're actually, since you're talking about pulling out as opposed to pulling in, you're going from a state in the parking lot that is in fact very low entropy to a state of very high entropy, which is you out of the parking space. So if you think about it that way, as the more ways I can satisfy the criteria of whatever it is, then the more disordered that criteria is, and therefore the higher the entropy is in that particular state. Whereas when I pulled it out of the parking space, there was even more different choices, so it was even more disordered, and therefore the entropy was an increase in leaving the parking space. So hopefully that will help you have some idea what we're talking about here. I'm just going to take this little, well, I'm going to erase this little parking lot, parking space, and my little rectangular car now that I've sort of explained that and give you some more information. So, for instance, one thing you could do, and your book does an example on this, an ice cube of mass 56 gram is taken from a storage compartment at 0 degrees Celsius and placed in a paper cup. After a few minutes, exactly half of the mass of the ice has melted, becoming water at 0 degrees Celsius. Find the change in entropy of the 56 grams of ice slash water. So really all you're doing there is doing dq over t in this case, or excuse me, q over t, because in this case it's actually held at a constant temperature. The temperature is 273 Kelvin. You got to remember that K has, or that temperature has to be in K kelvins, not Celsius degrees. So you could actually do that problem, but again, that's more than what I'm asking of you. I just want you to have some understanding of it. You can also do a treatment of, for instance, if you take let's say you take a 20-gram hunk of, or let's say even like a 75-gram hunk of aluminum at 100 degrees Celsius, and you pour it in, I don't know, 100 milliliters of water at 22 degrees Celsius. What's going to happen when you put that 100-degree chunk of metal in there is the metal typically will cool off and heat up the water, and the water, of course, is giving some of its or taking some of the heat from the metal to warm itself up. So you would end up finding, since water has such a higher specific heat than the metal would, you'd expect it to turn from maybe 22 degrees to maybe 24, nowhere near the 100 degrees that the metal was at. But without violating the second law of thermodynamics, if you really did do the calculation and you found that that particular metal was 75 grams and had a very specific heat that we used, and that it brought it exactly to 24 degrees Celsius from 22, then you could also equally, using the first law of thermodynamics, say that I put the 100 degree Celsius metal into the 100 milliliters of water. And instead of the 100 milliliters of water getting hotter and the metal getting colder, you could actually do a calculation and show that it's perfectly legal, according to the first law of thermodynamics, for the water to instead go from 22 Celsius degrees to 20 degrees Celsius. And then the metal will, in fact, go up quite a bit to some new higher temperature. So you could literally imagine a scenario in which heat is extracted from the colder water and put into the hotter metal, and the metal got hotter than 100 degrees, and the water got colder than 22 degrees, so that ultimately the water was 20, and the actual temperature of the metal might be as high as like 200 degrees Celsius now, if that's, below the melting point. So that's one of the neat things about entropy, because if you now go and do a calculation of entropy for that very exchange, which you can do for extra credit if anybody wants to, it's a very straightforward problem. We assign it even in our physics 201, 202 sequence as well. But in that case, what you'd see is the entropy actually decreases in going to that new solution that doesn't happen, and that's why specifically it doesn't happen. All right. Your book does take time to show that the entropy is a state variable. That's a really nice little quick and dirty derivation. But the most important parts I tried to highlight in the book, but I realized that this new electronic book does not highlight things properly. It keeps dropping it when you're in the middle of highlighting something. But there's a wonderful statement towards the bottom of page 589, I think it is. Yeah, I think it's page 589, where you're in the next to the last paragraph, and it says the integral of dq over t between two equilibrium states, between any two equilibrium states, A and B, does not depend on the path of the process. By defining entropy as ds equals d bar q over t, we see from the equation that the change in entropy between any two states along a reversible path is independent of the path between 2 points A and B. Thus, entropy is a state variable. Its value depends only on the state of the system and not on the process or the history of how it got there. This is in clear distinction to Q and W, which, remember, I told you you're not supposed to use a DQ or a DW unless you put a bar through it, because those are not state variables. Their values depend on the processes undertaken. So real processes are irreversible, but because entropy is a state variable, the change in entropy, delta S, for an irreversible process can be determined by calculating delta S for a reversible process between the same two states. So that's the key aspect that I think is most valuable about the state variable, is you don't even have to know what the process was. You can just make up a process that you know how to work out, as long as it starts and ends at the same state, which would be, clarified by like P1, V1, T1, and N1, and P2, V2, N2, and T2. If you had those variables and you found some kind of process that would go from 1 to 2, then you could use that to calculate the change in entropy. And because entropy is a state variable, you would automatically get the right answer. So, anybody have any questions about that?
No.
Okay. Now, entropy in the second law of thermodynamics, the book talks about that a bit. And ultimately, what they tell us, and you can look at all those examples, but those are beyond what I'm asking of you. But what they're trying to tell us is the entropy. We can thus make the general statement of the second law of thermodynamics as follows: the entropy of an isolated system never decreases. It either stays constant in reversible processes or increases in irreversible processes. So that's another general statement of the second law of thermodynamics. The entropy of an isolated system. Okay, that means it's not interacting with the environment at all. It's not just adiabatic, it's literally not interacting with the environment at all. Uh, that's why specifically, if you have in one area in an isolated system, you can actually have an increase in entropy, whereas the other area might show a decrease in entropy. And that is actually exactly how we did not violate the second law of thermodynamics when we were trying to assess the energy exchange while life was evolving, say. Okay. The total entropy of any system plus that of its environment increases as a result of any natural process. So when you, instead of taking an isolated system, if you take the total entropy of any system, isolated or not, plus that of its environment, increases as a result of the natural process, of any natural process. So the total entropy, like of the universe, for instance, is always increasing, but we can find areas where it doesn't increase, at least on an isolated system. Okay. Or excuse me, on a non-isolated system. So they talk about time zero. That's sort of helpful. Then they talk about tossing coins basically for order to disorder. And that's what I want you to read most of so you'll understand why S equals K ln of W is a definition of the entropy. They give us another second law of thermodynamics. It says natural processes tend to toward a state of greater disorder. That again is a general statement of the second law of thermodynamics. And in the section 20-9, I think it is. Oh, in any natural process, some energy becomes unavailable to do useful work. That's the process I was telling you about, how we think of heat as a bastardized version of energy, where once some number of joules are converted to heat, you're not going to get that same number of joules back out. There's going to be a smaller number when you try to extract it later. So yeah, section 20 dash, looking at it, 20-9 is where they talk about the statistical interpretation of entropy in the second law. And they start off with just, counting heads and tails of coins. So if you throw four coins up, I guess you could do all four at once, or you could do one four times. Then the odds of you getting all heads is one out of the total number of states that you could have thrown. So you could have thrown a head in the first one, or a tail in the first one, a head in the second one, or a tail in the second one, a head in the third one, or a tail in the third one, or a head in the fourth one, or a tail in the fourth one. But only one of those possible outcomes is one that has four heads. So the probability would be one divided by the total number of outcomes that you could have gotten. That's how we calculate probability. It's like the number of successes divided by the total number of things that could have happened. So, what happened that were success divided by, in the number of them, divided by the number of possible outcomes. And when they do that, they then go to proper probabilities of various macro states for 100 coin tosses. So they amped it up a bit and thought about 100 coin tosses. And when you do that, then you can imagine I'm going to toss 100 quarters, one, two, three, four, five, one after the other. The odds of getting 100 heads is so small. In fact, your book lists it as the probability as 7.9 times 10 to the negative 31. So that's just extremely unlikely, right? In fact, if you did it at a rate of one per second, it would take 7.9 times 10 to the 31 or 1 over 7.9 times 10 to the negative 31 seconds, which I suspect is comparable, if not, yeah, that should actually be older than the age of the universe. But if you think about it and say, okay, well, let's consider the microstate of 60 heads and 40 tails. If I wanted that microstate, it turns out there's a lot of different ways you can do 60 heads and 40 tails. It's still fairly low probability. Its probability is about 1.1%, but it is still a microstate. The macrostate really is the whole 100 results of, or excuse me, I should say, the whole number of results for 100 tosses. So if you toss 100 coins and calculate exactly how many outcomes you could have gotten from that 100, that would give you the total number of macro states, if you will. And then the individual micro states is the one, all the ways that it gave you 60 heads and 40 tails. Well, that turns out to be 1.4 times 10 to the 28th different ways you could do that. And if you divide that by the whole total number of outcomes you can get from throwing up 100 coins, the probability turns out to be 0.011. That's all shown to you in table 20-2. So the reason why I'm pointing that out is you'd take that, you know, traditional process where you'd say, okay, here's one coin. I'm going to make one purchase and it's got two outcomes, head or tail. And then for each of those, let's say this tail down here, there's a head or a tail. And then up here for the head, there's a head and a tail. And then for each of those, there's a head and a tail and a head and a tail. And you keep doing that until you have 100 different levels of the tree, if you will. Let me actually, instead of showing that in the air, let me give you an idea of what I'm talking about on the actual thing. So if we're looking at a coin toss, we can say, for instance, Here's a coin. The outcomes for that are head or tail. That's one toss. Now, if you do two tosses, you can get a head or a tail if the first one was a head. But if the first one was a tail, you could also get a head or a tail. So after two tosses, there's obviously four different outcomes that you can see here. One representing head head, one representing tail head, one, and I'm saying them backwards. One representing head head, one representing head tail, the next representing tail head, and the next representing tail tail. Let me show you how I got those. So this is head head, this is head tail, this is tail head, this is tail tail. So you can see there's one way, two ways, three ways, four ways that you can do two coin tosses. But now you've got to do even more because we're trying to get up to 100, not to two. So this one gives you a head and a tail, and then this one gives you a head, and this one gives you a tail, and this one gives you a head, and this one gives you a tail, and a head and a tail. So at three, we're up to one, two, three, four, five, six, seven, eight. We're up to eight. So you can see what we're getting at is two to the third. So by the time you get to 100 tosses, we should be up to two to the 100 power. So that would give you basically 2 to the 100 power because you can see the first one was 2 to the 2, which was 4. The first one was 2 to the 1, which was 2. So it does seem to have that pattern, and therefore you'd say 2 to the 100 is the total number of states of that macro state. But like I said, the 60-40, 60 heads and 40 tails, uh, there's only 1.4 times 10 to the 28th ways to do that. So the probability, what the book is calling this letter W, would be 1.4 times 10 to the 28th divided by 2 to the 100 power. And that would be the probability of a 60-40 split. Okay. And then, like I said, we go on to define the entropy as the Boltzmann constant times the natural log of that W, where the Boltzmann constant is the one 1.6806 times 10 to the negative 23rd joules per Kelvin. Yeah, I think that's what it is anyways. Let me double check. If I got so many numbers in my head right now, I don't even know what's happening. Anyways, let's see. Yeah, 10 to the negative 23rd. I just wanted to double check on that. Uh, for some reason, I was thinking of 8, but that's because we just finished working with the Stefan Boltzmann constant, which has an exponent of 10 to the negative 8. So that's it. That's the entirety of chapter 20 that I care about you guys being able to do. Does anybody have any questions on that? Okay. Well, we're going on into chapter 21. And chapter 21 is called Electric Charge and the Electric Field. And what I want to tell you a little bit about is charges. So it turns out there are, let me go ahead and stop sharing here because I don't need to write anything on this particular one. But it turns out that we discovered charge. I say we as a human species discovered charge literally thousands of years ago. Uh, not as easily as you might suspect, because in this modern world, it would have been really quick for us to discover it because all you have to do is swipe your feet across the carpet one time in the winter, and oh, lo and behold, you go to grab a doorknob and you'll get the crap kicked out of you. Uh, well, maybe not the crap, but it'll hurt a little bit sometimes. Okay, so that is an actual, more or less like a lightning strike. So what's happening when you do that is you've scuffed your feet against the carpet. Let's say you're barefoot and let's say whatever the major molecules are in your skin on the bottom of your feet, there's a good chance that those molecules have a higher affinity for the electrons than does whatever molecules are in the carpet. If that's the case, then what will happen is your foot scuffing across the carpet will suck those electrons, and it sucks the electrons because the electrons are the ones out in the outermost layer and tethered to the nucleus the least strongly. So it'll suck out those electrons, and then you will become electrically charged to the negative. So you would then be a negatively charged creature, and that negative charge, since like charges repel and unlike charges attract, all those negative charges that you strip from the carpet will try to orient themselves all over your body in such a way that they're the maximum distance apart, so that they're the minimum amount of potential energy stored up in having yourself charged. Now, that means I'll have sort of like little electrons, maybe sort of equally spaced all over my whole body. And then when I reach out to touch the doorknob, which is made of a metal, which is a conductor, conductors have this property where they don't hold on to their outermost electron quite as strong as other things. Those other things being what we would normally term insulators. But to be honest with you, it's a spectrum because there's metal conductors that don't conduct as well as other metal conductors, and there's insulators that don't insulate as well as other insulators. And in fact, if you're dealing with a really high voltage, something that might have been an insulator at lower voltage has now become a conductor at this high voltage. For instance, the Earth in our atmosphere, the atmosphere requires 3 million volts for basically 1 meter of atmosphere to become ionized such that lightning can strike. So if you have a voltage difference from 1 point to about 39 and an eighth inches away from that point, and the voltage difference is 3 million, then instinctively, basically, something's going to fire to equilibrate that. So what's normally going to happen if the voltage is high over here, a bunch of electrons are going to shoot towards it. Okay. So that's a case where air, which is a really, really good insulator, both in terms of heat as well as in terms of electricity, all of a sudden became a pretty good conductor, good enough to, get someone electrocuted in the case of a lightning storm, which is, why we have lightning. But when you do that with a light bulb, I mean, with a bunch of electrons on your body as you're reaching for a doorknob, what happens is your finger, which has all this negative charge on it, as it gets closer and closer to this doorknob, whoa, look, a magical doorknob just popped in. It looks just like a doorknob. So I go to grab it. What happens is the little negatives on the ends of my finger make all the little negatives that are free to move around in this metal, they make it run away to the other side of the conductor. And then this side of the conductor all of a sudden looks positive. So my little negative charges of electrons all over my fingertips are now seeing these little positive charges. So they take a leap of faith, specifically when the voltage difference per meter is 3 million volts per meter, boom, you get a little spark. And if you're actually fortunate enough to be looking and it's dark enough at the right time, when you actually have that shock hit, you can one hear a little pop, but in addition to that, you can see literally a blue flame of light, if you will. So that is something that happens with charges, and it's one of the things that we talk about as one of the concepts in this chapter. So I've put a series of videos in our module for chapter for this week and for next, and it's a bunch of videos where people are doing demonstrations at MIT, specifically physics demonstrations for their physics department, and that shows you a lot of the stuff that the author is talking about in the opening paragraphs of 21. What I want you to understand is there's a process of polarization and a process of induction. And the polarization is sort of like where the doorknob became a little bit positive on the side closest to me because it was polarized. The net charge of the doorknob probably didn't change at all until my electrons jumped off of me onto it. Uh, and that's the hallmark of polarization. We just induced a charge on one side without actually changing the charge. You can actually cause the charge to change. One way of doing that would be if you had a wire that was attached to ground, which in a light socket, of course, means this little hole down here at the bottom. If you had a wire attached to that little hole down there, then that's attached to literally a wire that brings it to a long copper plated rod that's I think code requires it to be at least 6 feet, but it might even be 8 feet, and it's nailed right into the ground next to your house, right where the electricity comes into your house from the power company. But if you did take a wire and plug it into there and then touch that wire to the doorknob as I was near the doorknob, then because I'm pushing those negative charges away from my side of the doorknob, those negative charges would go to the other side and they would actually continue going through that wire down to the ground. And then the doorknob would actually have a net positive charge. Then when I get near it, close enough to it where the voltage between the tip of my finger and the part of the doorknob that's closest to it, when that voltage is big enough for air to become a conductor, then the lightning will strike and it'll cause the electrons to jump over to the now positively charged doorknob. And in fact, it'll start to become less positively charged because the negative charges are just subtracted one by one, where we basically count the charges in increments of E, which is 1.602 times 10 to the negative 19th coulombs. So that's some of the neat stuff that electricity does for us. I hope you've all had a full life where you've done things like the one thing I really like to get my students to do, even though I can't really think of a good scientific reason to do it other than just curiosity, is I love advising my students to take a 9-volt battery and stick it on their tongue. Okay. It doesn't feel good. It's a little jarring, and if it's just a random 9-volt battery you find out in public, you're asking for some kind of communicable disease or fungus or something. So don't do that one. But anyways, if you do it, you will get quite a shock. 9 volts is pretty significant. And it causes you.
I do have kind of like a observation that I
Go
kind of
for it.
want to ask. There are occasions in my office where um like all of the everyone that I work with, whenever we touch the door frames
Hmm.
or anything metal, we're always getting shocked, but it's very temperamental.
Oh,
It's
really?
like on certain days. So I don't know if it's just like there's a lot of static in the air or what that case might be. But I
Right.
just didn't know if that had any correlation to kind of,
It
yeah, just like I don't know, electric fields that are in the environment or
it one thing during the winter, I would suspect it's going to be a lot worse. And the
because
reason
it's
for
drier.
Yeah, because it's drier. And that's not easily seen, but we did do humidity last chapter or chapters, I think it was 18 maybe, might have been 17, but I think it was 18. We did relative humidity. And the point that that makes is the humidity is a relative measure of how much water is dissolved in the air. Uh,
Right.
it has a maximum amount, and when we get to that, that's when precipitation occurs, which we call
Yep.
rain or snow or something like that. But the main thing is water are polar molecules. They're little. I try to treat them as Mickey Mouse ears. So you got Mickey
Hmm.
Mouse, oxygen atom, ear is a hydrogen, ear is a hydrogen. It turns out the oxygen being completely full by taking two of the electrons, one from each hydrogen, is way more energetically favorable than the hydrogens have in their own. So it turns out the electrons spend the majority of their time away from the hydrogen down this side, so you end up getting a positive charge sort of between Mickey's ears and a negative charge between on Mickey's chin, and because of that, the molecule is polarized. That positive end between his ears will grab any loose negatives every time. And that positive end or that negative end will also attract ions that have been made by losing their electrons. And so the more water in the air, the less you can get that. For instance, I've even tried to do like the Van de Graaff demonstration, where my hair stands up. Yeah. Where one of my students who has hairs will stand up. But in doing that in the summer, I often get my room so humid because I'm such a big guy with a lot of surface area and a lot of sweat that it gets too hot where even their hair won't stand up. So
Huh.
that's one thing. But the other thing is, yeah, if the room is dry, if it's really dry because you've got a good HVAC unit, they don't pay to heat up the water in the air because that would cost way more money and energy. So what they have in almost all HVAC units is a
Yeah.
dehumidifier of some.
Dehumidifier. Yeah.
Yeah, so that's sucking all the water out and then leaving you with dry air that can shock the poop out of you.
Because I
But
mean, there will be instances where I will get shocked when I touch the doorknob, walk down the hall and touch another doorknob, and
and
I'll
still
get
get
shocked
shot.
again.
Yeah,
Yeah.
yeah, it sounds like that's probably it. It's probably they just have a really good dehumidifier or a serious unit, AC
I mean,
unit
they
or
just
whatever.
replaced the HVAC system in there, so
Oh, really? So
yeah.
was it like that before or just since then?
Well, when we moved into it, into the building, they replaced it, so we don't know what the
Gotcha.
before conditions were
Gotcha.
like. But
I thought you meant like recently while you're working there, so you noticed an uptick. But yeah, I
no.
would say that's the likely culprit. Plus, I think you're working a lot with computers, and I think they offer a little bit extra static in the air just from
Yeah,
the
it's just interesting
electronics.
because like there's literally days where I mean we all just hear like just like the shock hitting all of our fingers as we touch everything. So, but it happens, very intermittently, but when it does happen, everyone's getting shocked. So I
All
just find
right,
it funny.
exactly. Yeah, that's cool. Yeah, we used to do the thing with balloons. So hopefully y'all have done that before, where you can take a balloon and rub it against your hair, and then you take the side of the balloon that you rubbed against your hair, and you bring that near even a piece of drywall or the ceiling drywall, and it'll literally just stick to it. So that's another type of process like that I think kids with a somewhat fun childhood had experienced that, and now you get to learn why. I did want to point out, we only got a couple minutes left as the alarm came up, but I wanted to point out the equations and the relevant stuff. So, one thing we're using is there's a fundamental unit of charge that we call E. So, I've now made the iPad visible again. That E is the charge of the electron, but it's also the charge of the proton. Both of them have the same charge but opposite in sign, and that charge is 1.602 times 10 to the negative 19th coulombs, which is not a unit you've used before, and it's named after Coulomb, the scientist. So that's the Coulomb that we're using. And the electron, like I said, has a negative one. And then there's an equation called Coulomb's law. Oops, I forgot that I already did that part. It's called Coulomb's law. And it looks just like the law of gravity. Dang it, I cannot write the W properly. In that, the law of gravity said the force of universal gravitation is some constant called G, the gravitational constant of the universe, times m1 times m2, which is the masses of the two objects that are attracted to each other, divided by the square of the distance between them. And it also included the caveat that the force acted along a line connecting the point particles m1 and m2 and was always attractive. Okay. If the particles were not point particles, then it would be along the line connecting the center of mass of M1 to the center of mass of M2. Here we get a very similar equation called Coulomb's law, and in this case, it's F is equal to K Q1, where Q1 is the charge of one of the objects, times Q2, where Q2 is the charge of the other object, divided by the square of the distance between them. And the Q1 and Q2 are point charges. So again, in this case, we have the force acting along the line connecting the point particles Q1 and Q2. But if they're not point particles, then you compute the center of charge by the same process you do with the center of mass. And you can then the line connects the center of charge of Q1 to the center of charge of Q2, and then the distance is the distance from the center of charge of Q1 to the center of charge of Q2. But in this case, it's not always attractive. It's attractive when Q1 and Q2 have opposite signs, but it's repulsive when Q1 and Q2 have like signs. So repulsive for like charges and attractive for unlike. So positive and negative. So like charges would be positive and positive or negative and negative, obviously, and unlike charges would be positive or negative and negative positive. So I think that's enough. I will tell you that I'm going to use a integrated form of this where I actually have a vector type equation so that I can show you how to use Coulomb's law to integrate stuff. We will. You've got to be able to make this equation into a vector. That's the key skill that you're going to have to do. So I'll show you a couple of those. You might even try to consider how strong the gravitational attraction is between the nucleus of a hydrogen atom and its one electron, and then compare that to the Coulomb force of attraction between that same electron and that same proton in the hydrogen atom, and then consider what the Coulomb force divided by the gravitational force is. And in some ways, you compare that, you only get on the order of 10 to the 20th, but in other ways, you can get on the order of 10 to the 40th. So that's a nice little extra credit problem you can do. It'll be in this week's module or wherever the Coulomb stuff is. So thanks for coming. Feel free to stick around, ask me questions. I'm just going to wait for the last person to leave in case you have any.
All right, thanks. I'm gonna split. I gotta go.
All right, thanks,
Have a
Josh.
good one. Have a good night.
You too. How about you, Matthew? You need anything? Have any
No,
questions?
I'm gonna head out too. Thank you. See you next time.
No problem. Have a good one.
Yep.
Okay. So as I said, for extra credit, you can consider the mass of the nucleus of the hydrogen atom, which is just a single proton, and the electron orbiting it in the hydrogen atom. That distance is called the Bohr radius, usually given the symbol A0, and that's the Bohr, as in Niels Bohr, radius, which he was able to predict, I mean, theoretically, even before we really knew it, but it's 5.292 times 10 to the negative 11th meters. That's the distance to the innermost orbital on the hydrogen atom. And what we want to calculate is F gravity, which is G mass of the proton, mass of the electron divided by A0 squared. And we also want to calculate the Coulomb force, which is K. I don't like K, by the way. I'll be using something else different, but I'm still going to give you K just because it's a lot easier sometimes to use it. And this would be times E squared. I do not plug in my signs of charges in the Coulomb force, and I don't recommend you do either. But it's going to be E squared divided by A0 squared, and the K is 9 point. Excuse me, it's 9.9. No, it's 8.998. That's what it is. Sorry about that. Uh, it's 8.998 times 10 to the ninth, and in this case it is newtons meter squared per coulomb squared, but K is also 1 over 4 pi epsilon naught, where epsilon naught is 8.854 times 10 to the negative 12th Coulomb squared per Newton meter squared. So for extra credit, you can calculate Fg, Fc, and then Fc divided by Fg and turn that in uh, for extra credit. I hope that helps. I'm going to go ahead and stop sharing and say bye-bye to my people. Bye-bye, everybody. Bye-bye, everybody out there that's not here now. End.